Before I begin, a bit of legal. These videos are made to support students of the chemical engineering curriculum at UC Davis while trying to have a mutually beneficial, free, open resource for the general public to learn about programming in a general sense without fear of intellectual property infringement or otherwise legal issues that come with creating these resources. Students have been provided the individual tools from proprietary code that allows for single iteration analysis. However, I aim to supplement that resource with the addition of explaining the data structure and offer ways to automate or streamline the process. In this video, I'll go over the following: a review of the data structure from Lab 1.1 and how that might differ or be similar to this lab, Lab 1.2. A generalized function in which I use inline and block functions to extract and output a blank for students to use in order to input the respective experimental conditions. In the scope of this video and the work that will be done moving forward, I will serve as the data engineer and provide blanks and clean data templates such that the data that's dependent on the student's experiment can be used for further analysis. I want to emphasize that at the time of the recording, creating these resources assumes that the lab has not changed. So the code is designed to be somewhat future-proof within reason. For example, this code and the similar code demonstrated for Lab 1.1 is able to do so for any number of trials, which means one group may be able to use this exact same code to extract any number of trials, which may differ from another group. Thus, this code is not hard-coded by any design of the experiment. In a way, you may consider this a similar experience working with other departments at a company responsible for creating software for your use. This will be a two-part video in which I'll go over the data table expected for students to deliver. In the next part, part 2, I'll go over the figure making and tips and tricks for creating that figure using a generalized example. Using the same workflow like before is a review for Lab 1.1. We see when we import the data, we have two conditions: voltage and temperature. Of those, the same three conditions, subconditions, conditions A, B, and C being hot, ambient, cold. Each of those, by the design of the experiment, once more, as I've noted in the caveat that the design of the code from Lab 1.1 and similar to this, any number of trials can and will be analyzed as they'll be averaged for analysis later on. But as shown for the data set that I was provided as a representative set, the experimentalist has, by design, opted to standardize 3 trials for each of these subconditions for the main condition, which can be either to voltage or temperature. And of each trial contains your commercial and homemade equipment. Similarly, for Lab 1.2, going rather top down, going bottom up for a moment here, we see that a similar analysis is being done for the commercialized and perhaps the homemade as well. What differs for each of those outputs is the relative sampling rate and collection rate that we're now interested in looking at. So this dotted line, in some regards, is a oversimplification of even this level of data structure being shown for one of the commercial or homemade equipment, as one of those particular equipment then branches out into its respective sampling and collection rate. In this lab in particular, we see a temperature change occur from ambient to cold, ambient to hot, or perhaps one may consider hot to cold or cold to hot. Likewise, cold to ambient, hot to ambient, as some sort of temperature change in which one can model. Hence part 2 of the video that I'll be making, which will explain potentially the thermodynamic and heat transfer of the material that you're analyzing, either commercially made or homemade, to model the step change in temperature, where temperature is a function in which time is a parameter. Like before, starting with file handling, we create a folder, Lab 1.2 in this case. or in this folder, because I will be going over parts 1 and 2. Parts 1 we'll say is the data table extraction in the deliverable that's being asked to be made. And so in this folder, we put our working data, and in some regards, because the zip is being unzipped and uncompressed, we can simply just rename it as the working copy, inherently keep the zip as the original, or otherwise, more appropriately, it would be to rename the working copy as the original. If your data is not zipped as is, then of course create a folder in which contains your experimental data. In this working copy folder, due to the complexity of having your ambient conditions, your temperature changes, ambient to cold and ambient to hot, within your working folder, it's be a good idea to create a folder for those main conditions. Unlike lab 1.1, in which we were able to analyze within this main folder, that was by the design of the code. In this case, we are simplifying that by the design of how we're handling in this folder. And so we create our ambient to cold, and ambient to hot folders that contains those respective conditions. As a simplification, any other files that are not relevant to extracting the data from, I like to just keep in the main folder in the working copy here. And again, let us not forget to place our Python script in the main folder, one level below where our working copy of our data is. By the design of the code, where relative to the location of this file, it will go into this folder and into these respective folders to extract the data. Opening our IDE of choice instead of Sublime as previously demonstrated. In this case, I'll be consistent moving forward with what students will be using and have used in the past in the class. Personally, I enjoy using Spider and its IDE as opposed to Jupyter Notebooks in the Anaconda package. So first, opening the PyScript that we've saved in the main folder. I want to demonstrate once you've run the blank template and the IDE has access to the main path. What you can do is check what files and folders are being accessed by typing ls into the console. In this case, we can see the zip folder, our PyScript itself, but more importantly, the folder it's which contains our data. The main reason I'm opting to actually run the code and execute is, as I mentioned, there will be 2 parts to this video, and I wanted to end this part of the video with a section break, denoted by a hashtag followed by 2 %signs. This will be important because in this example, for part 1 of creating the data tables, the packages that we'll need is simply just pandas, os, and natsort, which we'll need to actually install because of a interesting sorting issue that comes with the way that the files have been named, as shown on the left, relative to cold and hot. But more importantly, it's important to mention that the trial numbers and the file names have been renamed. And so originally the output from the software is not these convenient naming conventions. Similar to what was demonstrated on the PowerPoint, I generally like to write out a workflow, so-called pseudocode, which will outline a workflow and general structure and guideline that we can follow as we work through our code. And generally just writing our thoughts down. As we'll see, I'll try to explain the deliverables that we meet in this workflow. So far, we've handled the file handling, and next we'll be importing the data. The importing of the paths, as we see, similar to lab 1.1, the name of our folder is represented here. Once more, where a period summarizes the current folder path, as we see on the left here, relative to where this Py script is. We enter this main folder called lab 1.2 data underscore working copy. And within this folder, for example, as we'll see demonstrated on the console on the far right, if I cd, short for change directory, into that folder, we can see that in here, our ambient to cold, and ambient to hot folders, as you see on the left, are being accessed. And so within these folders, as we'll see with this forward slash in the console, which is represented in the string, to access the files within, for example, the ambient folder, the path itself will need a forward slash in order to then access these CSV files, for example. And so that was a quick crash course on the fly analysis on the front end, as we see on the left, and on the back end in the code that was demonstrated in the console of what is going on when we create a string path like this. And so conveniently, we're going to create a data table, which will take the average and standard deviation of the commercial and homemade equipment for the ambient to cold, and ambient to hot conditions. You can extend this into cold to hot, hot to cold, etc., to cold to ambient, depending on the name of the folders and how many conditions you have. As we'll shortly see in the design of this code, it's irrelevant to how many trials are in each of these conditions. So it is up to the user to keep track of which condition is what by simply the design of the file handling, by naming the folder in which contains the representative data. And so, with that said, this next two lines of code will take care of any fluctuations in differentiation between any one group. So if one group wants to do 4 conditions, this will loop the conditions, ambient to cold, in this variable containing your file or your folder names, and in the paths variable, the main data folder path is simplified and accessed into the respective conditions. As we see by running this example, the outputs from the paths are stored in such a way that, as we previously demonstrated, for as many conditional folders, there will be the representative path relative to where this script is being stored. And so this is the so-called dynamic coding method that limits copying and pasting and allows for rapid development of analysis. Next, this part was created in hindsight. However, we noted the similarity between the dotted lines in the presentation that I showed earlier, in which the oversimplification of the general data structure is that we're still expected to extract data from a commercial and homemade file. And so we can actually create a function called extract data table. In this case, it could actually be any name of the function, but as always, we create variable names and any naming conventions such that it is representative of what it is doing. And so in this case, similar to what we've done in the past, although this is a bit jumping ahead of steps 4, once again, this was created in hindsight while still meeting the deliverables as noted in the prompt on the outline of the experiment. We define a function in which its entry is the path, or perhaps a path, and that path will contain a CSV file. We know from the output of that file, from the sensor and the software and the design of the experiment, that a header of 6 will remove any excessive data that we may not need and skip to the appropriate column names and column titles that we then extract by calling through a function once more in case there's a typo and to limit any obscure characters that we can't normally type. Next, we simply just take the commercial and standard deviation. Next, we simply take the average and standard deviation for the respective commercial and or homemade equipment. Per lab 1.1, the same outputs apply. In this case, I had opted to use -1, and that's more of a Python way to extract from the last index rather than 3. This is just a different way of showing that. Next, rather than just having a whole bunch of numbers, we can set a inline function called setPrecision, which will centralize any changes to how we want to format our values that are going to be exported to the data table here. So setPrecision will simply use a single line or inline function rather than a block function defined as shown here in the extract data table. Lambda followed by your input parameter will then define your function, your inline function. As I explain and type this out, as I copy from another screen, what we'll need here is a string type denoted by the S here. And this is just a way of representing an input. And so the %sign is a placeholder. In this case, we're asking the format to be a string. However, we're asking the masking of our variable input to be a float, such that the float input has a number of 3 decimal places after the decimal, where the float with 3 decimal places is denoted by a number which I've asked to be n as an input, and this input will then be wrapped as a string. This is important when we set the precision because in hindsight I've defined a variable called append_me. A numpy array is actually not needed, where the variable trnum followed by blank we apply our set precision of our commercial average. As one can imagine, we can simply just copy and paste our commercial standard deviation and apply the set precision of now our homemade equipment average and our homemade equipment standard deviation. Before we forget, and like with any block function, if you actually want an output from our function, we'll need to return said variable or outputs that we'd want. Otherwise, without a return statement, this becomes void, and it's as if no outputs, but we're asking the function still to do something with the inputs here. So that is a key distinction between having a return here. For this next part, now that we've defined a function that will extract the commercial and homemade average and standard deviation and input it, or rather its output is formatted in this way. Again, this was created in hindsight, so it's a little bit confusing at this stage. So let me continue on and it will make sense hopefully in a bit. So for this next step in the workflow, we've imported our data paths as I demonstrated as shown on the right. For this next step in initiating the storage containers for analysis, I want to reemphasize that this section was created in hindsight, and upon recording, I recognize that the outputs of this may be a bit confusing considering I've designed the code as a thought experiment such that I've opted to create and then analyze the average and standard deviation for every condition that is being inputted as a folder. As we see, I've created a for loop where I and enumerate is the index, and the condition and enumerate conditions, as we see in the top here, is the names of our condition folders. This will be particularly useful, the I index, for when we're going through our paths, where we'll need index values 0 through n, where n is our number of conditions. And the name of the paths, or of our folders, that we've inputted here, which again, this is part of the dynamic coding model in which, for example, if someone has a fourth input called cold to hot, this fourth input will be tracked and analyzed. However, in this case, we do not have this condition, and so we carry forth with this generalization. This is actually a very interesting point of interest in some foresight, where one could note the average temperature that is reported and its associated standard deviation, how that might look on the visualized figure on the temperature change, despite modeling the temperature change with a modeling equation where temperature is a function of time. In this case, as I somewhat rant about this idea, it is not a good idea to consider this junk data, rather something to think about and its application and its meaning beyond just the numbers and data. And so moving forward to step 4, I opted to create a data table for each of these conditions. And so rather than just calling it a data table, a very important programming concept is something called scope. So we're going to leverage scope, and effectively what we're creating within a for loop or any loop in particular, we create an instance, and an instance just means whatever we do in this loop, unless we make it a global setting and that's accessible beyond the scope of this loop, whatever happens in here stays in here for its iterations as we create. This is similar to any block function that we define or any inline function that we define. The instance, for example, in Python, is denoted within a colon. And so in this case, we can consider this data table that we're going to similarly create like lab 1.1 in a dictionary sense, because that's intuitive to me, and I believe that is one of the better ways of keeping track of our data. But more importantly, we'll need this format in pandas, in which we'll create a data frame from this table, from this dictionary, to then export into our resulting report. An important note here is, in order to get certain Greek characters or otherwise characters we can't have accessible in our keyboards, we'll need to use Unicode or some other solution found on Google. In this case, the Unicode for plus or minus sigma for standard deviation is represented by \U00B12, or I guess it's B00B1, and then 2 is the, or rather, then \U Unicode for 03B4 is the sigma. So we will correct this here. An important note, suppose, is when we are looking for 2 standard deviations, this is the simple change that needs to be done. Simply multiplying the standard deviations by 2, and those values will be corrected. As I mentioned, like anytime I'm working with dictionaries, I often like to have a function call which takes the key values and limits any typos I may have downstream of creating this code. And so we can say in this next step we're now importing the data paths, but we're now completing them for future analysis to then extract, as we see in the workflow on top. This is a bit out of order, but as long as we meet all the deliverables from the framework as shown in the workflow, then everything will be okay. Next, it was logical to define a data path in which we'll extract from. The rationale for this following set of code, which is a little counterintuitive and something that's quite complex, is because once more the files that are being housed in each of these folders have been renamed, and so regardless of the names and their sorting, well, rather not necessarily the sorting, because I've opted to sort them naturally, and this is to say chronologically in some regard. What this particular function call is doing is it's going into each of these condition folders for root, where this Python script lives, that's the root, its directories, in this case the ambient to cold and ambient to hot, and within those the files. And so in os.walk, what this is doing is going into here, and it is going into each of these folders. Now, the reason why I've opted to do it this way is because, well, we need to count how many trial numbers there are in total. And so for as many files there are in a naturally sorted files, which is simply to say, and as you'll hopefully read in the natural sort documentation when installing this, there is an inherent issue with how strings are sorted chronologically rather than numerically. So natural sort is the solution in this case. So for as many files there are in a particular folder, if the folder, or rather file, ends with .csv, per the lab instruction, the professor has asked that the data be exported to .csv. However, you're not limited to .csv so long as the data structure and the exported data is of similar header number and title's name, well, regardless of the column name, the header number. If it ends with CSV, then we'll take the extracted data path and equate that to the paths that we're looking at / the file itself. And so this is effectively identifying the path for each of those files to analyze. And if the file itself is a .csv file, then trial number increases to 1. And so now we can extract the data from each of these files now that we have the full path for only when and if the file ends in .csv. Then this logic statement becomes true. This part's a little tricky. So for the index in a variable called index data table, and enumerate, which means for every value within our blank table, an index, an index 0, 1, 2, 3, 4, etc., where the index 0 is the value number of trials as a string housed in the index underscore data underscore table. Once more, to simplify this, the index 0 through however many there are here, for example 0, the corresponding index value 0 in our data table blank column is a string called number of trials. If we were to try an index of 1, then the corresponding index of 1, or the second value in this variable, is collection rate hertz as a string. We do this because, unlike arrays, because of our use of a dictionary, to my knowledge, and perhaps this is a good thought case for myself to consider using zip or a map, but nonetheless this still works, and this is a good learning moment for myself, is to consider that we're adding these values one by one, where the data table instance dictionary will require that we have a string input for those values, and for each of those we'll need to add our extract data table function, where the extract data path is its input for each of those trial numbers. Staying one level above the loop, staying within this for loop still. Notice that I'm not beginning to type outside of the for loop. Instead I'm paying attention to seeing that the for loop level for each of these conditions is at the same level as shown here. We're going to export the table now. So when we export the table, we'll need to make a pandas data frame, and in this data frame we are putting in our data table instance. The reason why it's called an instance, once more, due to the scope of this for loop, now that we're nearing the end of it, once this for loop concludes, as we'll shortly see by the end of this next line of code, this instance repeats back up to this for loop and becomes cleared, where these are our initial conditions. This concept becomes a little bit more tricky, but as engineers, we can see that this is just resetting our initial conditions to be 0, and so we do stuff with it later on. It's a more useful consideration when we're building out classes and init statements, as self-explained it is our initial conditions. So stable table instance with our column names that we've already established. As data table blank column title. We export the table. I export them to Excel. It's personal preference, where we ask that a string function is being made such that we can keep track of our conditions and perhaps appendices. And of course, not to forget our extension, where the index is false. We don't want to show that. It's not necessary, and it's unnecessary noise to the export of our table. And so when we run this, so the error that I've identified is I've mistyped my bracket, and post recording I've come to realize, and I've forgotten, that we actually do need NUPY, so that's a correction on my part. For those who caught it early, great on you, that we actually do need NUPY for calculating the average and standard deviation here. Otherwise, as we see on the left, relative to where the Python script lives. Often as a general simplification, I just like to have the name of the file we're trying to export in the same folder with this script, or otherwise I'll make a folder and say table outputs and put a // name of the folder that we just made, followed by the name of our Excel sheet and the following file extension. But in this case, for simplicity, once again, we're just going to name the file and export it into the same folder, since there's been a lot of this file handling and file paths that make this conversation quite difficult to have without any basis for experiencing that yourself. All right, and so when I run this, we can see that our tables have been exported, as I mentioned, into the same folder in which this Python script lives. And here I'll open table 1, where the condition is our ambient, where no temperature changes occur. And so the caveat that I want to make with the design of this code, and for reasons that I believe by taking the average and standard deviation and analyzing all of the temperature measurements, part 1 of this code is better applied for data and conditions where no temperature changes happen. As we see, the average and standard deviations are representative of something that has little to no fluctuations, as we see by the standard deviation. But before getting into the analysis, I want to circle back into more the data engineering and preparation of the file as we see here. Note that the plus or minus and lowercase Greek symbol sigma is appropriately formatted. And so I've left room for the students to experimentally keep track of their collection rate, sampling rate, and expected temperature. Note that depending on the freezing and or boiling conditions, that the temperature that is expected is dependent on pressure. Likewise with the ambient, please pay attention to the environmental control that you may be housed in and protected from in the lab. So that's something to be aware of as well. Now taking a look at the average and standard table for ambient to cold, for example. Once again, I don't believe it would be a good idea to consider this junk data and not to be considered. As a thought experiment, I opted to design the code in a way that analyzes the average and standard deviation for any inputs from that sensor for any condition, regardless of temperature change or not, for the user to understand and to see the data as we see here, as shown, and consider what the average means relative to the standard deviation when a temperature change occurs, whether this has physical meaning and practicality or not. As we'll see in the next part of this video, I think it would be a good thought experiment to consider what the average looks like and graphing the standard deviation onto a graph of the temperature change occurring and seeing whether or not it's useful or not. Though one might imagine it may not be, that is my current hypothesis. I think it could be a good thought experiment to seek this out, as despite saying ambient to cold, the average temperature for some reason here is the temperature change of 42 on average.